So differentiation and integration of power series. A power series can be differentiated or integrated term by term over an interval contained entirely within its interval in convergence. In the case of differentiation, an open interval is required. That's kind of like because the end terms on a function, if it stops there, it's like, how do you do the tangent? It's that kind of idea. So, if fx equals the sum from n is 0 to infinity of c and xn, then f dash x is, well, we'll look at what we're actually doing. We're differentiating the inside function. But girls, can you look at the limits of the sum? What happened? We're starting at, the first one we started at n is 0, right? And now we're starting at n is 1. Why is that? Yeah, that's true too, because when n is 1, you'll get the 1 minus 1 is 0. But also, why don't we want x to the negative 1? It's because this one here, when n is 0, you get c0 times x to the 0, which is 1. The next term, when n is 1, c1 x to the 1. Second term, c2 x to the 2. When I differentiate that, this one doesn't become 1 over x. This one just goes away when you differentiate. And then you get c1 plus c2x. In other words, I start at c1 now. So that's why we get n is 1. We start at n is 1. So that's something to think about. You have to be clear on that. Now, but the integral, we can keep it at n is 0. The first term of c0 here, when you integrate that, you get c0x. So 0 is staying around. Yes?
When you move from 0 to 1, does that only apply when the initial series you're working with starts at 0? Like, if it started at 1, would you have to shift it up to 2? Or is it just when it's 0?
Actually, if it's of this form and it started at c1x, c1 stays around in the differentiation, therefore you could stay at 1. So basically the lesson is, when you differentiate, n needs to start at least 1. Because you can't, it won't work. You don't want 1 on x, basically. You do differentiation. Okay, cool. When you integrate, however, you can still start at n is 0 because the c0 term is sticking around in c0x when you integrate. So let's think about that. C of 0 over 0 plus 1, which is just c0. When n is 0, x to the 0 plus 1 is x. Yes, that's the term there that we talked about that would be around. So that formula actually works. Is everyone okay so far? Yeah. So let's apply all that into this question here. I want to find the integral of all of that. Basically, I can apply the integral inside the sum. So I can rewrite this as the sum of, from 0 to infinity, and wait, can I use 0?
Yes.
Yes, because I'm integrating, yes. Of all of that stuff that's inside there. So negative 3 to the n, x to the n, over root n plus 1 dx. So it's the sum of all that integral, of those integrals, when it is 0 to infinity. Now, girls, I can take some things outside of that integral. What are they? Sorry? The square root of n plus 1, yes? And? Good, because the whole idea is it's in terms of x. I'm integrating in terms of x, so technically I don't care about the n parts. If they're multiples and I can take them out, I will. If there was a constant term, though, I have to keep that in and integrate it. So I can now rewrite this. Now, one thing at a time, just take it out of the integral. So I get root n plus 1, and then times 0 to 0.1 of just x to the n. Girls, can I take this out of that as well?
No.
Why not? That's in terms of n. I want all the n's inside the sum. Beautiful. So that's a good point to realize the difference there. Okay, now, well, that's an easy integral, isn't it? That's lovely. Let's just write n is 0 to infinity. I'll just copy, oopsie, that. I get 1 n plus 1. And then integrate. So now I could be doing brackets around all this, like for the sum of all of this. It's up to you, really. I'm not overly worried. What's the integral of x to the n?
X to the n plus 1 over n plus 1.
Beautiful. 0.10. Now, girls, what's something I could do? Basically, this n plus 1, I'm lazy, I'm going to take it out. What happens when I take the 1 on n plus 1 out? How could I rewrite this part here? Close, yeah, and then when I take out n plus 1, you get n plus 1 to the 3 on 2. Is that okay? So you could think of it as negative 3 to the n over, you could either put it as n plus 1 to the 3 on 2, or you could put it as root n plus 1 cubed. Do you understand that that's the same? Yeah. Awesome. And then I'm going to actually do the substitution over here. So I've just taken n plus 1 out. That's all I've done so far. And then I substitute. So I have 0.1 to the n plus 1 minus 0 to the n plus 1, and you can just write 0, which equals, so all of the 0 part goes away. So basically, I finish it off by writing the sum as, because I know, now there's a couple ways you could write it. Well, what do you think is going to be our final expression for the sum? Yep, so negative 3 to the n times 0.1 to the n plus 1 over root n plus 1 cubed. Now, girls, because this is not a limiting sum, that's it. That's basically it. We're done now. But can I just show you, girls, you know that 0.1 is 1 on 10? If you wanted, how would you use that? How would you rewrite it if you wanted to?
10 to the power of negative n minus 1.
Yeah, or 1 over 10 to the n plus 1. In which case, no, they're both correct. So you could rewrite it as negative 3 to the n on top, 10 to the n plus 1 on the bottom, and then the cube root of n plus 1 cubed. It's really just up to you which one you prefer, that one or that one. They're both correct. And that's actually all you had to do. They didn't say estimate the value of, they didn't say find the ratio or, ratio test or whatever. They just said find it. So basically what they really wanted us to do is express it as a sum without the integral.